Okay, so hello, professor. I'm going to present you the thesis that is named Development of a High Energy and Power Density Asymmetric Supercapacitor based on vanadium sulfide CNC nickel oxide and iron oxide TNT vanadium sulfide electrodes. My name is Emmanuel Cerri Saldana, and I'm here with my advisor, Rudra Kumar. Bueno, Dr. Rudra Kumar.
Yeah.
And let me.
My
This
name
one
is KUMAR, not double M.
no double M. You just one M.
Yes, only one M.
Sorry, I will change it. Well, here the introduction. Well, why supercapacitor are important, or why do we want to develop supercapacitor? Well, the main thing is that of the properties that supercapacitor possess, because as we can see in the chart of the right here, we can see where is placed the capacitor, and the capacitor are like the two plate apparatus, which have only electrostatic energy, and these have a really high power density. And what is power density? Is how fast it can charge and discharge. So here we have this property, and this is what makes the like supercapacitor so useful, because these kind of properties, and also because it have a much longer cycle life than of batteries, which can last up to, as we can see here in the table, to the to 10 to the 6 cycles in comparison with batteries that have like 10 to the 3. Now, why and what are the problems with supercapacitor? What are the things that we want to explore? Well, as you can see also in the graph, asymmetric supercapacitor are some here in the middle between power density and energy density, which is how much energy it can store. As you can see, batteries have a really high energy density, which allows them to store a really a comparable high amount of energy, and that's the reason why are the most used electrochemical device compared to asymmetric supercapacitor, and that what the research is trying to do is trying to achieve a higher energy density with a material that we are studying, that is the vanadium, nickel, iron oxide, and that kind of stuff. Well, here also in the table you can see like how going in comparison how much time it takes to charge and discharge, and you can see in battery it can take hours, and with supercapacitor it takes seconds to minutes, and equally in the discharging time, and that is why this kind of technology can really be useful in, for example, in electric cars or in any kind of device that that will have the capacity to charge in seconds or minutes, and not in the hours that a battery takes. Well, now I'm going to explain a little bit of the supercapacitor. Here in the right, it's a diagram of a supercapacitor which has two electrodes. That is the cathode and the anode, and both are in the supercapacitor are of porous material, and in the middle we have the electrolyte. They are both submerged in the electrolyte, which have the ions, and when we start like the supercapacitor, like when we connect an external circuit to the supercapacitor, the electrons of the will start flowing through the external circuit, and the ions will start flowing in the electrolyte, being the minus ion, that the ion with minus charge go to the cathode, which is the one with positive charge, and the ions with positive the charge go to the anode, which is the electrode with a negative charge. Now, this is like how a supercapacitor works, but it's more based in the EDLC, and the EDLC are the double layer supercapacitor, which only work with electrostatic charge. Now, there are other kind of supercapacitor. Here we have also the pseudocapacitors, which unlike the other one, this uses redox reactions inside the supercapacitor, making it have more capable of storing more energy. And also, combining these two, we have another type, which is the asymmetric supercapacitor, which uses both the pseudocapacitor and the EDLC properties. Sorry, the computer is a little bit slow. It doesn't Allow me to change. Okay. Well, I already explained a little bit of the types of supercapacitor, and here in the right in the diagram we can see how an asymmetric supercapacitor is based. In the cathode, we have a battery-like electrode, which has the mainly redox reactions, and in the right we have the anode, which is uh, the the one that have mainly the electrostatic energy charge of property. Commonly in the industry and in many of the research that is made, the anode is commonly made of a carbon material, for example, activated carbon or any other type of carbon due to the property that it possesses, and it's because it's really cheap. And here we have a little bit of more explanation of the ELC, that is the electrostatic part, where the ions go to the electrode, and with this, being this close to both the positive and negative signs, this is how the energy is charged through a electric field. And here, like the kind of pseudocapacitor the pseudocapacitor reaction that can be, is usually under potential deposition, redox, and intercalation, which means the intercalation is the one that the ions are literally like are inside the electrode material, making to have a higher energy density. Uh, it's again not yeah. Okay. So uh, so here is the problem definition: how to improve the energy density of the system. Well, to do this, we first have to analyze the equations are that mandate how the energy behaves, which is here that we have the energy density is going to be equal to 1/2 C, which is the capacitance times the voltage, the operating voltage of the system to the square. And how do we measure the capacitance? Well, the capacitance is equal to the N, which is the number of electrons transferred, times the Faraday constant over the M, the molar mass, and B, the operating voltage. So what can we do to improve the energy density based on these equations? Well, what we can do is we can see that the M is dividing the capacitance. So if what we can do is to find materials in the electrode that have a lower molar mass, which will make a higher capacitance and therefore a higher energy density. Also, we can see in the equation that we have here an N, that is the number of electrons, which can be improved by a higher number of electrons transferred from the electrode to the electrolyte. So we have to also search for a material that has a high number of electrons transferred during the electrochemical reactions. Also, given that these equations only happen in the superficial part of the material, it doesn't happen in the bulk. So what is more important is that we have to get higher is the superficial area, and this is mandated by the how the microstructure is enabled. For example, like we have nanosheets, we have like nanospheres or that kind of material that can make it have a higher superficial area. And also, given that we need an electron flow through the external circuit in the supercapacitor, we need material with high conductivity, which will enable a better performance. Now, why are we using the metal oxide like vanadium oxide or iodine oxide? Well, they have high surface area, they have a really high theoretical capacitance, and they are easy access and cheap. Well, what are the problems with metal oxide? Well, first of all, they have low conductivity compared to other materials. So if we compare them, like for example, some type of carbon material, due to the like large band gap that have the metal oxide, it have a much lower conductivity. You want
Are you
to?
recording this one? Are
Yes,
you recording?
yes, I'm recording. I think
Okay,
yes.
okay, okay. Sure. Good, good.
Okay, and okay. Also, other problem with the metal oxide is the uncontrollable volumetric expansion. What does this mean? That the electrons start degrading faster than it should be. So making that the property of the supercapacitor of being really long life, having a long life cycle to be like not happy. And also they have a slow ion diffusion. So this is the problem that we have to deal with. Now, what's the hypothesis of this thesis? Well, use of a novel chemical composite of vanadium sulfide with nickel oxide doped with CNT as cathode, CNT being carbon nanotubes, and a chemical composite for the cathode, and a chemical composite of iron with vanadium sulfide doped with carbon nanotube as anode. Will enhance the capacitance of each of the electrons and therefore the energy density of the supercapacitor. Okay. Let me, I think it's recording. Yes, it's recording. For a moment, I was scared. Okay. So, what are the research questions for this? Well, for the cathode, what is the most effective combination of vanadium sulfide and nickel oxide to lower the molar mass and to take advantage of the valence state of the composition? Given that the valence material have multiple valence states in the last layer of the bala the how to say well that have multiple electron states in the last layer. Well, for now, the same question, but with the materials that are used there. What is the most effective combination of iron oxide and vanadium sulfide to lower the molar mass and to take advantage of the balance state of the composition? Now, another question, but now dealing with the microstructure, is the carbon nanotubes the most effective microstructure to enhance the electrical conductivity of the electrodes? Or maybe there is another kind of microstructure that can make a better performance? Also, we have to take in account like the scalability of the project, which is the like main purpose of all of this after all. So, will the use of these materials facilitate the industrial scale-up of the supercapacitors? And what the most important one, which will this system increase the energy density of the supercapacitor? Well, now, here are some of the previous work that it has been done with a material kind of with the vanadium. For example, here we have in the cathode composition a nickel vanadium oxide with cobalt boride in nanocomposite with a specific capacitance that is really high of 1,789 farads over gram. That is the usual units that is used. And as you can note here in the anode is used activate carbon as also in the ultra thin and also in the ultra thin nickel vanadium. This is because active carbon is the most employed anode to do research and in the industry, and that is one of the reasons that the energy density is not like high enough because active carbon has a really will have a lower capacitance than the cathode, making that the whole capacitance of the electrode to lower by a really considerable amount. Well, here we have another cathode composition that is a Maxine with BS2. But this is another kind of supercapacitor, which is a solid state supercapacitor, which unlike the one that is with aqueous electrolyte, for example, or liquid electrolyte, here they use like some kind of gel to don't have like the liquid form. So here we have also a specific capacitance. They in this case use an anode composition, so an anode composition of iron oxide in and here you have the energy density. There are a really high energy density of this compare. Here you have another that is a ultra thin vanadium sulfide nanoplate, which in this case the difference with the one is that it's an in-plane supercapacitor, which means that it's a really thin supercapacitor that is made like for portable and flexible applications. That like for like a really to have a really small weight and size. So here, as you can note in this and in the other in play, which is the ultra thin and nickel vanadium double hydrox nanosheets, both of these have the highest specific capacitance of this of this one of here, getting this of the last one to almost 3,000, and and this is because of the specific surface being really high due to the specific microstructure. Like in this project are really thin nanosheets. So this is the one of the reasons that this capacitance is much higher than in the other one, because here in this case they are using a nano flower, they have nano composite, so the microstructure can have a really high impact in the final capacitance and therefore in the final high energy density. Well, this is of the some things that have been used. And well, what we are going to do to elaborate the process is through a hydrothermal process. What's a hydrothermal process? Well, here's a little bit the picture of how it's going to be. So here we first we have to that solution with maybe ethanol or ionized water, ionized water in which we for example, for the well, here is no nickel oxide, is nickel right?
Nitride or sulfate, nitrate, nickel chloride, nickel salt.
Yeah, nickel salt, no, it's not a nickel oxide, it's nickel salt. So I'm going to change that later. We are also introducing the urea, that is the sulfide. Where we is going to we are going to extract the sulfide component, and here we have the vanadium salt. Well, we're going to stir it in the solution. We are going to add the functional carbon nanotubes. Here are functional carbon nanotubes because normal carbon nanotubes doesn't have is the functional groups to react with the components, so they cannot be attached to it. So here we first have to functional the CNT with some functional group like an hydroxide or something like that, so we can add it to the solution and it can stick to the CNTs. Now, here is the part of the autoclave. That is where we put the nickel foam, which is the substrate of the solution, and also other source of nickel. And here we put the solution, the nickel, and we heat it to 180 degrees for 24 hours. And this time will be also better. Is for example, for our example. And finally, we oven it to dry it, and we have the cap composition. For the anode will be something similar, just using the component of the anode. That will be the iron, or the iron and the other materials. And also for the electrolyte, we'll be using an aqueous electrolyte, given that, or for example, or other kind of electrolyte that are organic or that kind of stuff are really expensive, and the aqueous is more accessible and can be used for this kind of capacitors. And that'll be it.
Okay, so I have some suggestions regarding that. So when you are adding the capacitance for the cathode material, so in one slide you should add the capacitance for the anode material, like what is the capacitance for like activated carbon, what is the capacitance for iron oxide, what is the capacitance of some composite material that contains carbon plus iron oxides, like that. And then you can show that these materials, why you are using a combination of mixture of the material in anode, because suppose carbon, the activated carbon has a small specific capacitance like 200 farad per gram, or iron oxide has higher capacitance, or some another material, the composite material has high activated, high specific capacitance. So, like a literature review, as you did for cathode material, so you should also do one literature review for like anode materials.
Okay, okay.
Correct?
Yes.
And another thing, you prepared the slide. Go to the next slide next. Yeah, so this is the synthesis protocol, how to do the synthesis of the material and how to deposit the material on a conducting substrate. So after that, you need to make one or two slides how to do electrochemical characterizations, like how will you test your supercapacitor. So
Okay.
for that case, you need to make one more slide, like uh, you have three electrochemical system, and you will put some electrolyte on the beaker, and you have the electrodes, reference electrodes, counter electrodes, and working electrodes, and you will do some characterization like cyclic voltammetry or charge discharge method. Correct?
Mm.
So you need to put one more slide and just show them like you will do like that.
Okay, okay, okay. Yes, I will add it you also.
And if you want to do for the asymmetric capacitor testing, so for asymmetric capacitor testing, you can put two electrodes, okay, and in
Mm.
between that you will put one separator, and then you will add electrolytes, and after that you have to club them and then do the charging and discharging, like that,
Mm.
so that you can prepare a full supercapacitor which is in asymmetric form. So you can put one more slide on that.
Okay, okay.
Correct?
Yes.
So that is the final. And apart from that, Yeah, you already mentioned that in your literature review that why are you using vanadium or nickel or carbon nanotubes. So for your thesis, you need to do some proper, not proper means a comprehensive literature survey for at least 20 to 30 review
Mm.
like papers, and then you can compare what is the material, what are the combination of the material, what is the capacitance, what is the energy density, what is the power density, and take one difference. So if you want to publish a paper based on that, so this will help you to collect the data, and
Mm.
you can compare your results in the future with the current literatures.
Okay.
Correct?
Yes.
So that is my suggestion.
Ah, okay. Thank you very much, Professor. So let me stop recording.